This lecture is on optimization, especially as it pertains to architecture. This is Architecture Club. This lecture was written with PC in mind. Probably a lot of it applies to consoles, but I've never worked on consoles, so I cannot verify that. What optimization work have I done? I did optimization on Run Apocalypse, Perspective, Nous, and I just do it all the time. That's kind of what I do. So optimization, as they say, everything you hear about optimization is a lie. Not necessarily true, but that's the mentality you should have. Optimization changes pretty fast. A lot of, like, from a year-to-year basis, things will go out of date. They won't be true anymore. They might not be true on older hardware, or it might change depending on what hardware you're using. It's especially why I put the whole PC thing, because anything I say here is probably not true on consoles. Don't micro-optimize. I'm going to be talking about macro-optimizations here. Micro-optimizations are changing little bits of code, not changing algorithms, not changing data structures, not changing like big things of how you're doing things, but just little tiny things in the code, tweaking with assembly, won't really gain you much at all. Use a profiler. I'll be talking more about those. Those can show you where your bottlenecks are, what code's hurting you the most, so you're not just guessing. And also a big question is, are you GPU bound or CPU bound? And I'll be talking more about that. So the key with all programming is just thinking about a problem. So when you approach a problem, you have to think, what's the fastest way to do this? And I mean that in a developer time sort of sense. So what is the fastest way I can complete this problem myself? Like, how can I write this code and have it done as fast as possible? Then another question is, what is the probability that this will need to be optimized later? You can look at physics. If it's a no of n squared algorithm between 1,000 objects, if you don't optimize this now, you'll almost definitely have to optimize it later. If you just do your graphics without thinking about optimization at all, it's pretty likely that you'll have to go through and optimize that later. So then you have to think about what's the cost to optimize this now versus later. If you write a broad face that isn't very good and it takes you a lot of time, well then that's wasted time if you have to go and write a whole new broad face later. So if you're not going to optimize something now, you better be able to be doing it fast. And think about how much longer will it take to optimize this, and if it won't take that much longer, then you could consider just go ahead and do it now rather than later. It is better to push optimizations till later because you don't know where you'll be needing them. Especially you won't know if you need them CPU or GPU. But you have to make sure, how can I support future optimizations? If you write an interface, there is a possibility that that interface will not support optimization. So you'll write code, everybody will start using it, then you'll be like, oh, I need to optimize this, except the interface that you've made and now everybody's using, there's no way that you can write optimization that still conforms to that interface. So now you're having to go and change people who are using your code. Maybe it's not even possible to optimize anymore. I'll be talking about that more. Optimizing can hurt. So it complicates your interfaces. Often simple, easy to use interfaces are not very optimized. You can see this in languages, like a very easy language to use is Python, also one of the slowest languages ever. Languages that are a little bit more tricky, difficult to use are often very fast, so it's these trade-offs. It's time consuming. Programmers will often spend way too much time optimizing, and often when they don't need to, or it's not helping at all. Decreases your code legibility. Even if it's code you don't think people will be seeing very often, they probably will see it eventually, and if it's super optimized, it's going to be hard to read. Not optimizing can also hurt. As I said before, you may have to change interfaces. So one example is if I have an interface that takes all strings, and then I figure out that taking all these strings is too slow, and now I want to take like IDs or something, well now everybody who's using strings is going to have to change that, and maybe you just can't do that, especially if you're writing an engine where a lot of people are potentially using it, changing an interface that way just might not be possible. You may have to rewrite a lot of code. If there's like internally, if you wrote a graphics engine and you didn't optimize it very well, and now you want to go through and optimize this graphics engine, there's a possibility that there will be a lot of code internally depending that you'll have to update, make better, code that wasn't assuming all these changes that will have to be going down for optimization. Also for graphics, you may have to change the visual look of the game. There's a possibility that the way you wrote it just doesn't work, so you'll have to change the way the game looks. Like you had too many lights. Turns out you can't even optimize it so all these lights can work. You're just going to have to start removing lights, and then it's tricky because the artists have to take into account that you're removing all these lights. Maybe normal mapping is too expensive for you. Now your artists have made all these normal maps, and you're just going to have to remove them because normal mapping can be fairly expensive, or SSAO can be very expensive, so you can't rely on these things. If you had thought about optimization a little bit more up front, maybe you wouldn't back yourself into a corner like this. And because of these limitations, maybe you won't be able to optimize. Maybe you just can't remove normal maps because it'll make your game look horrible. So now you can't optimize that, and you're just going to have to bite the bullet and have a game that doesn't run very fast. Choosing an optimization. Before you make an optimization, you have to make sure it'll work. I've seen a few people, or I myself, have seen an optimization. I'm like, I'm pretty sure that works. It seems like it's going to work. And then I write it, and it doesn't work at all. So don't go off your hunches, and be skeptical of any resources you have on the internet. They might be out of date. They might be talking about a different hardware. It might be somebody going off their hunch and they haven't really researched it. You don't know. So try to prove it. Memory is very easy to do. So you can often calculate memory usage just with a calculator. If you know you're going to have like 10,000 of these objects and you know what their size is, just go through. Often I'll do this with broad phasing. Like if I'm making a gigantic grid and I know how many cells I'm going to be having, I'll just plug it into a calculator. Will this grid be consuming too much memory? Things like that. Very easy to do, so you might as well just go ahead and do it. There's been many times where I've had an optimization in mind that was sacrificing memory for speed, and then I looked at it and it's like, man, this is going to be taking 20 megabytes. That's not sure if I want to take that hit. Broad phasing can be difficult to test. Broad phasing is another really important optimization, but it's one thing, and there's a lot of optimizations like this where you don't know how much it'll help until you actually do it. So one thing you can do is think about best case and worst case scenarios. So broad phasing is, say you have collision, and you don't want to test collision of every object against every other object, so you try to make it so you only have to test collision against objects you're close to. So you can kind of eyeball the broad phase, and you're like, what's worst case scenario? Well, if they're all on top of each other, you're going to have to check collision against every single one. And then you can think about the best case scenario, where your broad phase calls everything. One thing I've done is I said, man, it would be really nice if my broad phase could make it so every object only had to check against 3 others. And so I wrote a quick program that would tell me about how fast that would be. And it turned out that was too slow too. So it's like, oh man, I guess even if this broad phase works as best as I can possibly imagine it, it will still be too slow. And all I had to do was like have a for loop that did it however many times I calculated and do a few dot products in there, just to kind of get a feel of, even if the broad phase went as well as I expected, how long that would take. So you can try to write a simple program to test how long a best case and worst case will take. Just try to make it so it doesn't take too long, but you don't want to jump into something without having an idea of how well it's going to work. So I'm going to talk about data structures here. So here's some data structures. There's much more. Unsorted array, sorted array. I broke this apart. Because unsorted array, you can remove all of one. Hash map or hash set, slot map, intrusively linked lists, and trees. These are big ones to think about, and these ones where if you don't know all these data structures very well, you should probably learn them, because these are the go-to ones for me. And a lot of other data structures are just kind of combinations or kind of derivatives of these, especially trees. There's a lot of different types of trees, but they're all fairly similar. So each of the structures you saw back there solve a completely different problem. So you want to learn each one, and then when you see a problem, it'll be pretty obvious which one to pick, because they are all different. And if you see that you think two could be solving the same problem, it's probably not right, because they're all completely different, and choosing should be fairly easy. And often the most optimal is also the easiest to use. Like if you need a dictionary sort of thing where you give it a key and you get back a value, hash map. It's the easiest to use, and it's probably also the fastest. If you need a list of things, array tends to be easiest, and it's also the fastest. So optimizing in the easiest way is usually the best way to go about it, at least from a broad sense. Because you don't want to spend a whole lot of time optimizing something, because then that's time that you can't spend optimizing the next problem. Because once you optimize one thing, there will be another thing that pops up. And if you spend all your time on one thing, then you won't have time for anything else. So some questions to ask is, can I solve this problem in a different way? A lot of times we'll kind of get our heads stuck in one way of doing things, and we don't ask questions like, do I even need to be doing this? Like, can I just not do this at all? Can you apply a broad phase? So instead of, like in physics, testing every object against every other one, can you only test some, try to figure out which ones are close? But that applies to a lot more than physics. There are times where in graphics too, you can broad phase to make sure that you're not drawing things that are outside the screen and doing that efficiently. Can I pre-process the data I'm using? This is one thing where if you're doing calculations over data, setting up that data so the calculations are faster sometimes helps, not always, but it's one thing to think about. Can I LOD, so level of detail? We often think about this in graphics, like if there's something far away, you use less triangles for it, so it runs faster. You can use it in a lot of things. Like in physics, if something's far away, you could have its physics be less accurate. Or AI, if an AI is far away, you could have them be a little bit stupider. A lot of people think about this in terms of graphics, but it can be applied to almost anything. And then there are other questions, like am I using an API incorrectly? There are a lot of APIs out there. You kind of have to know what makes them tweak, because if you do the wrong thing to them, they just might run really, really slowly. I'll show an example of that later. And then, am I just doing something else completely wrong? You could just be, you wrote an algorithm and you just wrote it incorrectly. So those are questions to ask. So this is an example of one optimization I did. So it was in Run Apocalypse. We wanted a large amount of cubes that bounced around, looked cool, and collided with stuff. So I actually, I'm going to pull up. So I went into the calculator, and first I was like 25,000, and I knew the cubes, so they needed like 12 bytes for position, 12 bytes for velocity, 16 bytes for rotation. Should add that all up. You multiply it, so 24, about 48, and then divide that by 1024. That's how many kilobytes we have. 11 megabytes. So that's actually a lot of megabytes we're seeing here for these cubes. So right off the bat, I know maybe this is just too many cubes. So maybe this is not even a problem I want to solve or can solve. There might be ways I could compress the position or the rotation or the velocity, but then decompressing it's going to be slow. So right off the bat here, I've just done a quick thing with the calculator, and turns out this might be an impossible sort of problem. So maybe I should go to my game designer and say maybe only 100,000 cubes. Then the other thing I did when I was approached with this is I just had a for loop. I did the thing where I'm like, so best case scenario, I want all these cubes to be checked against each other. Now I'm going to have a crazy broad phase here. So what if I get a really super awesome broad face where every cube only has to collide against one other cube? So then we have 250,000 collisions. So I already had the collision code, and I just ran it 250,000 times, and it was too slow. So even if I have an incredible broad face, this is going to be too slow. That test didn't take very long to write because we already had our collision code. And I figured out, so not only is this taking a lot of memory, it's also, there's just no way I can broad face this sucker. So the cubes, they're not going to collide against each other because there's no way I can do that. But maybe I can find something else here to do. So they can collide against the ground only. Or they can only collide against the ground and the player. That helps a lot. So that's what we ended up doing. Right now they only collide against the ground. And the cubes are also so small that we only check 3 points on them. So one that's near the bottom, one that's near the left, and one that's near the right. So they're so small that you can't even see that we're making, it's kind of a level of detail sort of thing. You can't see that we're doing that because they're so small. And then every time they hit something, we just kind of rotate them a little bit randomly. And you can tell a little bit, like there's some things that aren't natural, but when the player's playing the game, they don't really care. All these cubes go flying everywhere. They're colliding with the train. That's all the player really sees. And so I kind of have this problem, and I didn't actually do it. I kind of took a step back, and I realized that this is an impossible thing to do. And then you just have to talk to your game designer and try to figure out something that's going to work. Ooh. Need to get back in presentation mode here. So that's all been about thinking about optimization like while you're writing code. But there's a lot of times where you have a game and it's running slowly and you've already written the code. Now you have to go in and optimize it. And this actually happens a lot. It's almost the preferable thing. You don't want to be thinking about optimization too much while you're writing because profilers are so powerful. So the first thing you have to do is determine a CPU-GPU bottleneck. Basically, you can think the CPU and the GPU are running simultaneously. And so at the end of the frame, they both sync. So if the CPU finishes first, then it waits on the GPU to finish, because it can't start the next frame until the GPU is done. If the GPU finishes first and the CPU is still going, then the GPU has to wait for the CPU. So if you optimize the wrong one, let's say the CPU is waiting for the GPU, and I start optimizing the CPU, all it's going to be doing is making it wait longer. So you have to figure out which one's your bottleneck and then optimize that. So then you profile the bottleneck, and profiling the CPU and the GPU is two different things. I'll talk about them both. And then optimize in the easiest way possible, as I said before. So I'm going to go over profilers for those of you who haven't heard of them. So a profiler is something where it looks at your code and it'll tell you what your bottleneck is. And I'll show an example of that soon. But what the sampling profiler does is it'll probe your call stack repeatedly. So every few milliseconds, it'll say, give me the call stack, give me the call stack, give me the call stack. And then it can look at the call stack. After it gets all these samples, it can figure out where you're spending most of your time. Because if it asks for the call stack and every single time it asks for it, it's in graphics, well, that means that you're spending a lot of time in graphics. It's very nice. It gives a percentage of time spent in each function. It can't tell you how much time exactly was spent there, because all it can do is give you these percentages. It's using statistics, basically. It is nice because it's fairly accurate and it gives helpful results. It's not actually changing your code. So in contrast to the next profiler, it's more accurate, but it still can change your performance, because this will usually cut your frame rate in about half, is what I've seen. And so sometimes in doing that, it'll change your performance and then you'll get bad results. You just have to be aware of that, but I haven't seen it happen very often. You also have to run it for about 30 seconds so it gets enough samples where the statistics are correct. Some examples are Very Sleepy, VTune, and Code Analyst. This is an open source one that's Intel's and AMD's. And they're all very good. I use Very Sleepy because it's free and very easy to use. But the other two are more powerful and definitely worth looking into. An instrumenting profiler actually inserts timing code into your application. So like every function, it'll put code at the beginning and end to time how long you are in that function. This can give you exact measurements. So it can say like you spent so many milliseconds in this function, which the sampling profiler can't do. The problem is it's a lot more likely to change your performance. And so it's a lot more likely to give bad results. The nice thing is it does give the timing. So the sampling profiler, the downside is, let's say you need to profile your load times. So your load times take a second to run. And that's a long time for load, especially if it's in a place where it doesn't really messes up the flow of the game. But a sampling profiler needs to be run over 30 seconds. So there's no way that you can profile that load time with a sampling profiler. So you have to go to an instrumenting profiler, or you can just insert timing code yourself. Is kind of an easy way to do this sort of thing. The other thing is all graphics profilers I know are instrumenting. Just how they are. So NVPerfed, Nsight, gprof, and Valgrind are two CPU side ones that are instrumenting. So I'm just going to give a demo of Very Sleepy here. I couldn't actually run it on this computer because this computer's old, but I was able to run it on my laptop and then save the results, and now they're over here. Basically what it looks like is, I can't show you like beginning to run it, but it'll give you a list of all your processes, and you click one, and you can click a thread, and then it just spins for a while, and you hit OK button. It's all pretty simple. So here we see a list of all the functions, and I've sorted them here. Ooh, I can't actually see that on this projector. Let me actually. Yeah, now we're in here. So exclusive is the time spent in this function and only that function, whereas inclusive is the time spent in that function and all of its children, which I think is a lot more useful. So you see like win main here, 0% exclusive because we don't spend very much time in main. But in inclusive, it's near 100% because we spend a lot of time in its children, actually all our time in its children. Sometimes it's a little bit silly and it doesn't have 100% here. Sometimes it'll say like 50%. I don't actually know why it does that, but you can just kind of ignore it and imagine that it's 100%. So here's our core. This is for Rhine Apocalypse. And I actually modified the code a little bit. This is not, I put some bad stuff in here to make it more interesting. Because, so here we can click on core run. It's nice to start from like your loop. And we can see down here, not sure if you can read it, but we can see graphics system, physics, action manager. So here's all our systems. I see 84% of the time was spent in graphics. So we know where a bottleneck is. 9% spent in the message manager, 4% spent in the hardware input. Now that's a little bit weird because it's just input. Why is it taking 4% of our time? It's not a huge bottleneck, but that's a little bit confusing to me because I think input should be fast. So I can just click in here and go in there and see now set controller rumble, 51%. Well, that's a lot. Go in there a few more times. X input set state. It's taking a long time. And if I poked around a little bit more, I would realize I can go back up the call stack here. That get controller state, our other one that's taking time, is X input get state. If anybody's used X input, you may have run into this. If you try to pull a controller that does not exist, it'll take about a millisecond to do that. That's a long time. Here I found that I am pulling controllers that don't exist. Unfortunately, I can't open my code, but there's this if statement where it asks, does this controller exist? I just kind of commented that out, so we're pulling controllers that didn't exist to give a nice little example of something that's going wrong here. Unfortunately, graphics tends to be pretty hard to profile with Very Sleepy because it's a GPU sort of thing. But I go in here and I notice that there's a Windows Sleep that's taking 22%. I put a sleep 8 in there just to make things funny. So there it shows up. Whoever put that sleep in, just remove that. It'll be a little bit better. If I look in end scene, well, that's not very helpful. This is all like DirectX stuff. If you see numbers like that, it means they couldn't load the symbols for it. Does that a lot with graphics, but hey, we're not using the right profiling for graphics anyways. That's how it is. Funny thing is, when I put that sleep in there, our FPS went down 2. Because Rhino Apocalypse is a very GPU-bound game. So the fact that I was waiting there, it doesn't really matter because directly after that, I was just going to wait on the graphics card anyways. So the sleep actually did nothing. Shows that if you optimize the CPU while the GPU is blocking, nothing's really going to happen. Because I just put a straight up sleep 8 in our graphics code and only lost 2 FPS from it. So with that said, we should probably talk about determining your bottleneck because you want to be able to figure this out. Putting a sleep is not the greatest way to do this ever. One thing you can do is decrease your resolution because that means less pixels are going to be processed. That doesn't affect the CPU very much, but that'll speed up the GPU a lot. So if you increase the resolution and your frame rate doesn't go up very much, that means that you're CPU bound because you just made the graphics card's life a lot easier, but your frame rate didn't go up. Yeah? You could be Vertex bound. That's pretty unlikely. This next one, this one's nice because it requires no tools. This next one does require tools, but it's basically like how you figure it out if you really want to. You can use NV-perfud, which I'll be talking about later, and you can tell it to ignore all draw calls. Basically, it's like, hey, GPU, do nothing. And so the GPU just starts doing nothing because it's just ignoring everything you say to it. And then if your frame rate does not go up when you do this, you are definitely CPU bound because the GPU is doing literally nothing. It's pretty nice. I found things where I didn't think it was GPU bound. And I did this, and it turns out it was CPU bound, and I was pretty sure that it was GPU bound. The thing is, graphics can, yeah? You can do that without tools as well, right? The thing is, draw calls can take a lot of CPU time. So like if you just comment them out, then you're going to be speeding up your CPU too. So that's the thing. Like if you just, like in Rhino Apocalypse you saw there, 80% of the time was spent in graphics. That doesn't necessarily mean the GPU is the bottleneck though. Because graphics can be very expensive CPU-wise too. Draw calls, all that API overhead, it can really bite you. Like if you're doing like 3,000 draw calls, that's really going to slow you down. So even if a lot of your time is being spent in graphics, you could still be CPU bound. And then you just have to make better use of the API. You have to make fewer draw calls, fewer state changes. You have to switch shaders less often. The draw calls are the big one though. This will keep all the CPU work still going, where the GPU just does nothing. That said, let's talk about using NV-perfud. Unfortunately, it can be rather difficult to get it working. On my laptop, it won't work unless I have a monitor that's above 1080p attached to my HDMI port. That's how it is. The reason for that is because I have an Intel card, and the only way to stop the Intel card from running, I have the Intel card and a dedicated one. The only way to stop the Intel card from running is to attach a monitor that's above 1080p to the HDMI port. That's how it is. There will be weird things with your computer too, I guarantee it. There'll be different weird things than with my laptop, but you'll have to figure it out. Desktops tend to be a lot better, but laptops can be bad because they don't test it with the mobile graphics cards quite as much. It's also a little bit outdated, which is why it doesn't support Optimus on my laptop, which is the problem. Doesn't work well with OpenGL, if at all. Apparently it's kind of supposed to, but not really. Even with all of those, it's still awesome. As I said, I wasn't going to try to run it on these computers because that wouldn't have worked. So I just took some pictures of me in perspective. This is after I did some optimization work in perspective. So when you boot up NV-perfud, it will kind of go into your game screen. It gives you all these fancy graphs and stuff. Really useful ones are over here. This is your memory usage, so like 180. So we're using 180 megabytes on the graphics card. That's pretty good. Textures, render targets, and buffers. So we can see here the red is textures. That's almost all of our memory usage. So if I'm worried about memory, I shouldn't go chasing after buffers or render targets because the textures are a problem. Yeah? No, it's a tool. You do have to put a little bit of code in your application to hook in so that you can't just go run this on anybody's game. You have to have code that lets you hook into it. Read the installing guide and I'll walk you through that. Up here we can see how much time is spent in the pixel shader versus the vertex shader. It's all blue. You can't really see the vertex shader. There's like this thin red line down here which is the vertex shader. This is what you're going to see most of the time because there's a lot more pixels than you often have vertices. Down here we have some more graphs. I don't find them as useful. You can read about them in the NVPerfug guide, but I'm going to keep moving because I don't use them very often. So we can see these buttons down here. If I hit frame profiler, we're going to get a lot of really cool information. So here it shows all of what it calls state buckets. And so these are organized by like which render targets we're drawing to, which vertex shaders we're using. So everything in this state bucket will be using the same vertex pixel shader and drawing to the same render target with the same basic information. And down here I can see all the draw calls in that state bucket. This is the really interesting stuff though. We can see the red bar is how much time was spent in this state bucket. So we can see that top state bucket, and it sorts them based on how expensive they are, took a lot of our time. And then this other bar is the draw call in that state bucket. So this top draw call is a really expensive one. It's taking almost half the time of that state bucket. Then we can see input assembly, geometry, shader. Now we can see most of our time is being spent in shaders here, so I may want to start optimizing those. Textures, that's how much time was spent reading from textures. Raster optimizations or operations, that's how much time was spent writing to the buffers. And frame buffer too. So if I'm going to start optimizing this, I probably want to be looking in the shader. Now if I look over here, it shows what percentage time was spent in each sort of shader. Again, all pixel shader. That's to be expected. That's how it usually is. Yeah?
Explain what input assembly is.
Okay, yeah. Input assembly is taking your vertex buffer and converting it to a format that the graphics likes. That's the kind of simple way of describing it. So there is a way where you can have like two streams of vertices and then have them combined by the graphics card. That's when you're going to start seeing the input assembly go up, is if you have two streams and then you have to combine them. Normally you do that with instancing, but you could be like, hey, I'm going to have my positions in one stream and normals in another, and this going to combine them. That's a horrible idea. Don't do that. That'll make your input assembly shoot up, and probably your geometry more expensive too. But if you see input assembly high, it's probably instancing, and you might want to just consider not hardware instancing anymore, for those of you who know what that is. But it's very unlikely you'll see that unless you're doing kind of advanced graphics stuff. So there's this advanced button down here. What that should actually be is like, show me more useful information, because it's not advanced. It's just like something you always want to click all the time because it's useful. So if I click that, it shows me the mesh that is being drawn for that draw call. So that was my most expensive draw call, and now I have a better idea of what it's drawing. Any ideas of what this is? Yes, it's a point light. If you're doing light prepass or deferred lighting, a lot of those things, you're going to be drawing your light as geometry. So this super expensive state bucket is probably lights. So now I know what's hurting me so much. It's all those lights. So now I can see my vertex shader and pixel shader here. So if I click on those, I'll bounce down, and now I'm looking at the Vertex shader. I can see its assembly. If you use DirectX load from file, it'll actually put the file there. If you open the file yourself, it doesn't know the path to get the file, so it won't be able to show you the file. It's a reason to use DirectX create from file rather than opening it yourself. It's just tools like this. But anyways, it's a good thing if you're going to be a graphics programmer to learn how to read GPU assembly. It's pretty, there's not too many instructions. Pretty easy to get a hang of. And so I could take a look at the Vertex shader, see if anything silly is going on. And there's a lot of other so, I mean, that's most of the useful stuff with perfud. I mean, it just tells you what your most expensive draw is, what part of that draw is so expensive. Yeah?
You said it doesn't work well with OpenGL. How bad is it?
I have not actually tried to use it with OpenGL, but I heard Sean Middledish did, and it, like, yeah. Have you tried? Yeah.
I've tried it, and I never got it to work ever.
Yeah. I would be.
I never got it to work in general. Trying 3D or OpenGL.
Yeah. It's hard to get to work with either, but like I try so hard because it's really awesome when you get it to work, and there's not too many other tools like this. There's another one, a new one, Nsight, which apparently is better, but I can't get Nsight to work. I can get perfud to work, but I can't get Nsight to work. I tried for hours and hours with Nsight, and I just could not do it. So if you can't get perfud to work, you can give Nsight a try. Didn't work for me. Anyways, some other perfud tricks is, as I said, you can have the GPU ignore all the draw calls. You do like Control-N to do that. They have all these like keystrokes that have no GUI. You just kind of have to read their manual to figure them out. You can switch all textures to be 2x2 dummies. If you have really big textures, then that can start to get expensive. So if you're worried that that might be hurting you, then you can do this, and now all your big textures are very, very small. And if your frame rate goes up a lot, then maybe you should think about starting to reduce the size of those textures. Or if you're not mapping them, you should probably do that. This is also cool. I've not tried this, but I was reading the manual like yesterday. And it says that you can edit shaders on the fly. So you can edit them and then go, and it'll still be running. Thought I would throw that in because if it works, it's super cool. But if it's like a lot of other perfud stuff, it probably doesn't work. But they try, like, yeah.
Honestly, the ability to hot swap shaders is something that you're going to want to do if you can.
Yeah.
Just yourself, not using any tools.
Yeah. Yeah. Hot swapping shaders is super awesome. If you can get NV perfud to do it for you, though, like, sweet. I mean, ooh. So I'm going to go a little bit. I told you like how to identify the bottleneck. Now that you know have to know how to fix it. So we now know what our bottleneck is. And so what if you're geometry bound? So this is the graphics card, like not even the shader, the graphics card doing stuff with vertices. So you just have way too many vertices. This is not likely going to be your bottleneck because pixel shader usually is. But you're going to have to try frustum or occlusion culling. So just giving less vertices to the graphics card, some sort of LOD. So if things are far away, you draw less vertices. Decreasing the triangle count of your mesh, just telling your artists, like, you're giving us models with too many tries, you're going to have to try to decrease that. Any other way you can think to decrease the vertex count. Another thing is the size of your vertices actually does matter. The GPU has a vertex cache of 32. So it likes vertices that are 32 or a multiple of 32. That said, it likes 16 and 8 even more because those are small. So basically try to make it smaller. But let's say you have like a vertex size of 40 and you just can't get it any smaller. Bump it up to 64, assuming that memory isn't a concern, because 64 will actually be faster than 40, because it aligns to the cache. And this is true across many cards. I've seen it in many different presentations from Intel, or not Intel, NVIDIA and AMD saying to do this. And there is vertex compression. So there's things called half floats, which are half the size of floats. And the graphics card supports them. So like for your normals, they're only between like -1 and 1. You don't need that much resolution. So you can use half floats. And now you're cutting the size of that in half. So if you're looking for a way to reduce the size of your vertices, look into the compression a little bit. Geometry bound. Oh, whoa, didn't go to the next slide. Input assembly bound. As we were saying, with input assembly, if you have multiple vertex streams that then get merged, that's where this is going to hurt. So basically, you have a vertex declaration, which is basically telling the GPU how to take your vertex and convert it to the format that the GPU likes. It's basically telling it how your struct is laid out. If you're input assembly bound and there's probably something insane going on with your vertex stream or declarations, because it's in charge of handling them. Also, if you just have a ton of vertices, it might show up here too. Vertex shader bound, another unlikely one. You have too many vertices, or your shader is slow, or both. So any of the previous vertex, like culling, just getting few vertices will help this. Optimizing your vertex shader will help. I'll talk a little bit about that. This is very unlikely, though. This is super likely. Pixel shader bound. As you saw, that's where perspective was blocked. Rhine Apocalypse is pushing tons of vertices, and it's still pixel shader bound. We're a voxel game. We have a lot of vertices. I thought we were going to be vertex bound. No, pixel shader bound. So even a kind of pathological case of vertices, you might still be seeing pixels. Because when you think about it, there's a lot of pixels on screen, especially when you're running at like high resolutions like 1080p. So some things you can do is a Z prepass, which is you render your scene only writing to the Z buffer. And then if you draw again, it will be able to tell that objects who are behind other objects, it won't even go into their pixel shader because they'll get called out in what they call the high Z. Also, in light prepass, you usually draw your scene once. Make sure you keep your Z buffer around and then keep it there for your second pass, because then if you draw an object that's behind another one, like I said, it'll notice that it's just not going to be drawn at all because of your Z buffer, and it won't go into the pixel shader. Occlusion culling, this is a CPU side thing. If CPU side, you can tell that an object's just not visible and you don't draw it, that's going to help a lot. Sort draw from front to back, this is another Z buffer optimization. If I draw this mouse before the table, then I'm going to be drawing the mouse, and then the table's going to be going over it. If I draw the table first, then when it goes to draw the mouse, it'll realize that it's not visible because of our Z buffer, and it won't go into the pixel shader if we're lucky. It is a little bit graphics card dependent and high Z dependent, but it's a good thing to try. Merge with another pass. Sometimes you can do this where you have two shaders, and you can just kind of merge them, which will help. It's not too often that that's the case, but if you're drawing like two full screen quads, sometimes one shader can just be inserted into another. Using a different algorithm, like if you're doing forward shading, where for every object you compute every light, you might want to look at something like light prepass, where you kind of turn that on its head, and the lights kind of only affect the pixels where they're actually going to, that are close to them. Optimizing your shader, I'll talk more about that. This is kind of like something you should go to last. I like doing it, but it hasn't proven very effective to me, optimizing shaders. Optimizing assembly is super fun, but changing your algorithm completely will often have more results unless you just wrote a horribly optimized shader and you did something that just completely angered the graphics card. Yeah? Oh, yes. Yeah. So the Z buffer is a very delicate thing, and as you notice here, like, it's important. So yeah, like writing, as he said, writing to the Z buffer. So there's a way where you can just write directly to the Z buffer. That will anger it. If you search like graphics cards optimizations, there's a lot of like little small things like that that I can't even begin to cover here. I'm trying to get like big, like high level things. Using smaller textures, if you're like pixel shaders doing a lot of texture hits, that's going to be expensive. If those textures are smaller, it'll help a lot. If you can reduce the number of hits, that'll help a lot. Another stencil call. That's a pretty advanced thing that doesn't happen very often, but something to be aware of. Raster frame buffer bound. Use fewer multiple render targets. There's a way where you can write to multiple render targets like from one shader. So that's basically like writing to 3 textures at once. That'll be fairly expensive, especially on cards that don't have as much memory. Decreasing the size of your render targets, decreasing the bits per pixel of render targets. So just choosing a texture format that's more compressed will help. Consolidating passes, so you're not writing, so you're just doing fewer passes of shaders. This is very unlikely, but we're going back into like unlikely things. So here are some other tools. I really like these tools. These are the kind of like I need to optimize some assembly tools. Shader Perf and AMD's GPU Shader Analyzer. And Intel GPA is Intel's new tool that's kind of like NVPerfUD that I also couldn't get to work. Ta-da! There's a lot of tools that are like NVPerfUD that I totally can't get to work. But it exists. It's out there. I'm going to talk about NV Shader Perf and GPU Shader Analyzer. The tricky thing is when you're optimizing shaders, it's very difficult to tell if you're actually doing good because there's so many graphics cards out there, and I've optimized this, it will generate assembly. Like you can take your HLSL, the shader code, generate assembly from it, but then the graphics card will take that assembly and generate more assembly. So if you look at that assembly, that's not actually the assembly that's going to be run. So I have cut my operation count in half once in this assembly, and then I actually ran it, and it was like 5 times slower. And I'm like, what happened? Well, I made that assembly language better, but then when NVIDIA tried to generate their assembly from it, it must have choked and just had a really hard time. These tools will help you get around that. So, let's go here. I have a shader here that's very simple, but it could use some optimization. It is a pixel shader, so I'm just normalizing the normal I'm getting from the Vertex shader, and I'm taking the depth and I'm dividing it by my far plane. So I probably want depth to be from 0 to 1 instead of from 0 to far plane. One thing is, graphics cards can't divide. Maybe some of them can't, but as far as I can tell, they don't like it. So what they'll do is take the reciprocal and then multiply it by it. But that's an extra step you have to do. So if instead I had passed the reciprocal far and then multiplied by it, that would speed it up a little bit. And I ran Shader Analyzer, and it confirmed that it would actually speed it up. But there's a thing that I can do instead. In my Vertex shader, instead of passing 0 to far plane to my pixel shader, if I move that division to the Vertex shader and then pass the pixel shader 0 to 1, then I don't even have to do anything in the pixel shader. So there's a lot of times where you can, if you see you're just doing a multiplication or a division like this on a value you're getting from your Vertex shader, you can usually just move this multiplication or division to the Vertex shader, and then not every pixel has to do that. And so here I have the outputs. So I have this tool that just dumps the assembly and also runs the NV Shader Perf and AMD's. I like NV Shader Perf a lot more. You can download it, read it. Basically what it'll do is, so it says 6 instruction slots used. That's the first assembly language I was talking about. Then it converts it to NVIDIA's, where it says 3 cycles and 2 RRegs. So that's what really matters, is this, the cycles and RRegs. And then it tells me how many pixels it can do about. And so this is on a G70, so pretty old. And then I do it again on a G80. You see the cycle count and the RX goes up, but the G80 is so much faster that it just kind of chews those up. And it's actually a lot faster than the G70. And then down here, I do it on 2 AMD cards as well. And their output is a lot harder to read, but like these are the numbers we're looking for. And then so I ran it on, so if we just remember these numbers, like 32, lots of pixels, 3 cycles, 2 RX, and I ran the other shader through it. Ooh. 5 instruction slots, so we went down a little bit. This still has 32,000, so actually not much happened there. And then 12, yeah, go up. But that went up, so we went from 9 to 12 high digits. So the G80 is a little bit faster. Nothing happened to the G70 though. So sometimes you'll do things that you think are like super cool optimizations, and then like nothing will happen to one of the cards, or it will go down and you'll be like, what happened? So it's really important to run a tool like this to make sure that what you think is an optimization actually is, yeah.
So is it like emulating graphics cards?
I don't really know. I didn't read that about it. I just kind of trust that it knows what it's doing.
Also, like, is this all the NVIDIA tool?
Yeah, so
And do you have
this is actually 3 different tools. I use FXC to generate the assembly, which is Microsoft's effects compiler. Then I use NVIDIA NVShaderPerf for this. And then it's not letting me scroll down anymore. Oh, mouse is dead. Oh, no, it's back. OK. And then the AMD one for this. And I just have a basically Python batch sort of file that does them all for me. I will post that. I'm not sure if I have the rights to post the actual executables, but I can post the Python file at least that automates it. Yeah. So now we've seen those, you don't have to go optimizing HLSL code and actually hurting your performance. Now you can have some hard numbers to back that up. And that is it. There's lots more to be talked about optimization, but I don't want to bore you. I've gone about an hour now, so if there's any questions, be happy to take those. Yes?
You said it was NVIDIA shader.
I will go back up. NVShaderPerf.
Is that like the NVIDIA perf kit, or is the...
Oh yeah, I should have mentioned. This is going to be hard to find. It's out of date. It was made in like 2008, and apparently they don't want people to use it anymore because they have made it very hard to find. But if you search like NVShaderPerf 2, I should have put a 2 on there because apparently adding 2 to it makes the Google search work. If you don't have the 2 on there, you'll not find it. I don't know, whatever. It is out of date. The AMD's is a lot more up to date, but really, if you think about it, you want to be optimizing for older cards anyway, because those are going to be people who have trouble with your game. And the 7 series and the 8 series aren't that old. I do wish they would keep it up to date because it is such a useful tool, but what you going to do? Yeah?
A lot of these are from NVIDIA. Do any of them favor NVIDIA graphics cards, or is it all...
Oh. So the question is whether they favor their own graphics cards, and they probably do. Yeah.
I work on like AMD.
I have actually not tried NVShaderPerf on AMD. I imagine it would still work, but I'm sure they both. Well, I mean, NVShaderPerf only gives you the results for its cards, So it's basically favoring itself because you're not getting the readings then on AMD's cards, so you're optimizing for their cards only. If you run both of them, it helps, though AMD's output is so much harder to read that I don't use it as much just because it's lazy. Yeah.
For Z buffer optimization, you mentioned drawing from front to back.
Yeah.
Is there a similar technique you can apply on transparent objects?
So the question is whether there's a similar, like for the Z buffer, drawing front to back is good, but transparent objects or non-opaque objects, you have to draw back to front, basically. And so no, there's really nothing you can do with those. Because if you're thinking about it, the whole optimization is that you're drawing something in front so you don't have to draw the thing in behind. But with transparent objects, you do have to draw the thing behind. So that's just not an optimization that applies to those. You'll find transparent objects are kind of a performance pain. Huge performance pain. Especially when you get into looking into light pre-pass where it doesn't even work on them. They're nasty, but that's what you got to do. Okay, thank you. If you have any questions anytime, come ask me.